Good evening. Welcome to the live interactive session. I am Rahul Chaudhary. I am a PMRF NPTEL TA for this course, Analysis and Design Principles of Microwave Antennas. Here, every week we will meet around at 4 o'clock and we will solve few problems based on the content available on the current week. And the idea is of this session is to help you in solving the assignment problems for the current week. So I will be solving today some relevant questions which are related to the topics covered in this week. So if you have any doubt during the problem solving session, you can unmute yourself and ask while we are solving the problem. So first we will start with the topics which have been covered in this week. So topics covered in this week lectures are: first it started with the radiation, then vector potential and scalar potential. So vector potential we saw A, which is magnetic vector potential. Scalar potential is V. Then we saw solution of inhomogeneity. Then we saw Helmholtz equations, singularity extraction, induction field, dipole field, far field, power pattern, plane wave structures, and far field and Fraunhofer, Fresnel Fraunhofer zone, and E plane and H plane. So what the major concept that we saw in this week lectures are: we saw that we we uh, selected a quantity called A, which is magnetic vector potential. If we want to find out the E field, radiated electric and magnetic field from a source, let's say the source can be a current source, it has current density or a magnetic current. Now if we want to find out the radiated field because of that, radiated field means H field and E field. One way is we can directly find it out using the Maxwell's equation, but it's too complicated. A lot of integrations are involved. So in order to simplify this calculation, we selected few quantities called vector potential, which is A and F. And from this we can calculate the radiated field. Yeah, good evening everyone. Welcome to the course. This is a live interactive session for the course Analysis and Design Principles of Microwave Antennas. Those who have just joined now, we were discussing about what have been covered during this week's lectures. So the idea of this interactive session is problem solving session is to solve few problems which are based on the content covered during this week, and the idea is to help you in order to solve the assignment problems. So the problems will be similar to the assignment problems but not the same. And in assignment problems, most of the problems are numerical, MCQ based, and they are numerical, like you just have to put a formula and find it out. But here we will be solving few derivations also. And these sessions will be helpful if you watch the whole lectures for that current week. Then it will be really helpful for you. So I hope everybody has already seen the lectures taken by the professor. I am a PhD scholar taking uh, taking the live problem solving session. So I hope if you have any doubt, you will unmute yourself and ask. It's open to everyone. Everybody can unmute and ask the question which is being solved. So I was discussing about the topics that has been covered in this week. So the main concept that was covered is we find it out. We selected few quantities known as we saw some quantities called vector potential. So why do we need that? Because let's say a source is there which is radiating the field, and we know the source can be a structure, a metallic structure, let's say something like this, one antenna, maybe a wire antenna, a dipole, and any kind of antenna which has a current density on it, and we know that what is the current density. Now we want to find out the radiated field, which is electric and magnetic field due to that source. Now there are two ways to do that. There are two ways to do that. We can directly find it out using the Maxwell's equations, or but which is very complicated. A lot of calculations are involved in that. But and then there is a second option to use vector potentials. That's why we define vector potentials, which will simplify the calculation for us. So what is A? Is magnetic vector potential. So I'm not going to cover the theory just as a first lecture. That's why I'm giving some brief idea about them, which has already been discussed by professor. So my job here is to solve the problems. So we will be solving soon. We will start solving some problems. Just a basic concept. I'm a kind of a revision I'm doing here. So that's why we use this magnetic vector potentials. I hope the idea is clear. Now we will move on to solving the problems. And just a second. And you guys are free to unmute yourself whenever you have doubt. You can ask me. So now we will start solving the problems. Question number 1 is a horizontal infinitesimal electric dipole of constant current I naught is placed symmetrically about the origin and directed along the x-axis. We have to derive the far zone fields radiated by the dipole, and also we have to calculate the directivity of that antenna. What we have given here is a small dipole antenna is there, which is oriented along the x-axis, x, y, z. So the dipole is oriented toward the x-axis. So whose length is L. So this is L by 2 this side and L by 2 this side. Now we have to find out the far zone fields radiated by the antenna. So what is far zone fields? Far zone fields are for which K into R is more than the lambda, like whatever the distance is. Let's say suppose we are calculating it at some distance R. Its points are x, y, and z. It should be greater than like few times of the lambda. Should be greater than lambda, or we can say few lambdas, where lambda is the wavelength of the field radiated by the antenna. So let's start solving this. So here what we have given is a source is given. Source is given in the sense we know there is a current I naught flowing in that dipole antenna. Now that our next step should be we have to find the vector potential, because we want to find the radiated field. So in order to do that, to simplify the calculations, we are going to find the vector potential, magnetic vector potential A, and from that we will calculate radiated fields. Radiated fields are electric and magnetic fields. So in the problem, it's given that the dipole antenna is oriented along the x-axis. Let's suppose this is our dipole antenna. L by 2, and also this side it is L by 2. Now we will calculate magnetic vector potential due to this antenna along x, y and z direction. Now we know that since our antenna is oriented along the x-axis, the vector potential will also be along the x-axis only, because the current is flowing along this direction, which is I naught. So which is given by mu by 4 pi into minus L by 2 to L by 2, because it's symmetrically oriented around the y-axis along the origin. So this is L by 2 in the plus x direction and L by 2 in the minus y direction. So that's why this integration is from minus L by 2 to plus L by 2 I naught e to the power j k r divided by r, which is oriented along ax dx. So we can write this as ax cap is a unit vector along the x-axis, mu 4 pi r. I naught also is a constant, so we'll take it out. So we have to integrate now minus L by 2 to plus L by 2 e to the power dx, because e to the power minus j k r is also, we can write this as r. Here r is what, x square plus y square plus z square. So r is a position in the free space, and that whose coordinates are x, y, z, and its distance from origin is r. So now we can write this as we are denoting it as a small r. So this r also e to the power minus j k r integral between the limits L by minus L by 2 to L by 2 dx. Now when we solve this integral, we will get the magnetic vector potential due to the dipole antenna, ax cap mu I naught L by 4 by r into e to the power minus j k r. So now we will let this as our equation 1, because now whole idea was to find the vector potential, so that now we can calculate radiated fields, because in the problem we have been asked to solve for the radiated fields, right? So now the next step is to find magnetic field and electric field, magnetic field and then electric field, using the equations H is equals to 1 by mu into del cross A. I hope everybody knows how this equation came, right? If you have any doubt in this, you please ask me. It's all been taught in the first lecture of this week. And the electric field is given by minus j omega E minus j 1 by omega mu epsilon del into del A. Now we will transform the equation 1 from rectangular, now it is in rectangular coordinate system. We will transform into spherical components. Then we can easily use the equation number 2 and 3. So transforming equation 1 from Cartesian or rectangular to spherical components. Then use equation 2 and 3 to calculate the radiated field. So here we know that since the antenna is oriented along the x-axis, the magnetic vector potential along y and z are going to be 0 in this case, because oriented along the x-axis. And we know how to transform a rectangular coordinate system into the spherical coordinate system. It is given by AR, A theta and A phi, which is equals to sin theta cos phi, sin theta sin phi, cos theta, here cos theta cos phi, cos theta sin phi, and minus sin theta, minus sin phi cos phi, and 0. I hope everybody knows this. AX, AY, AZ, but AY and AZ here are 0 for us in this case. So now we can easily write this ARS AX sin theta cos phi, because when you multiply this and the other two components here, AX is equals to 0, AZ is 0, so these two will be 0. Similarly, A theta will be AX times cos theta cos phi, then the other two are 0, that's why, and A phi will be minus AX sin phi. So now using the equation number 2, we can write the magnetic field H as so equation 2 was 1 by H is equals to 1 by mu del cross A. So 1 by mu, now del cross A is, we can write this in spherical coordinate system, AR A theta A phi. So I'm writing that now, 1 by mu. Now I am taking the curl of this A vector, which is given by mu r square sin theta into A r cap A theta r sin theta a phi cap, dou by dou r, dou by dou theta, and dou by dou phi. I hope everybody knows this. A r a theta. So nothing special. I'm just taking the curl of a vector which is written in the spherical coordinate system. R sin theta a phi. So I can now write this as h vector is equals to 1 by mu r square sin theta. Now what I'm doing is I'm writing this ar a theta a phi in terms of ax a in its rectangular coordinate system. So what I'm doing is now I'm writing the ar a theta and a phi value here. Ar cap r a theta cap. So if you guys have any doubt what we have done till now, you can unmute yourself and ask. Dou by dou r, dou by dou theta, and dou by dou phi. Ar is ax sin theta cos phi, and a theta is r ax cos theta cos phi, and r sin theta a phi, so which is minus r sin theta ax sin phi. So now when we solve this, we will get, now I am writing the components, because if we see h will have three components, a plus, like this something will be there, right? So I am writing the component which is along the r, which is 1 by, it will be something. Yeah, if you have any doubt, please let me know. Rakesh Panda. So here it should be negative, right? So we can write this as, I'm writing the h along the r component, mu r square sin theta ar cap. Yes, here, and so same thing, right? Dou by dou theta of minus r sin theta ax sin phi, and minus dou by dou phi of r ax cos theta cos phi. And now when we calculate this, we will get mu r square sin theta, when I do this partial differentiation, I will get minus r ax sin phi cos theta plus r ax sin phi cos theta, which will cancel out, and the hr component, the magnetic field along the r direction, is 0. Now we have to find out the theta and phi component. When we calculate in the similar way, we will get h theta s minus I naught L to the power minus j k r divided by 4 pi into gk by r plus 1 by r square sin theta. So I think up to this it is clear, right? If you have any doubt, please ask me. Now we will calculate, similarly we can calculate hv, which comes out to be minus I naught L e to the power minus j k r divided by 4 pi into j k by r plus 1 by r square cos theta cos phi. Now we are going to using del cross H is equals to j omega epsilon E to calculate the E field. So ER will be 2 eta I naught L e to the power minus j k r divided by 4 pi, which is 1 by r square plus 1 by j k r cube sin theta cos phi. So if you observe, this ER component is not 0 in the near field. Right now I am writing a general equation for the near field. Then E theta will be eta I naught L e to the power minus j k r divided by 4 pi into j k r plus 1 by r square minus j by k r square cos theta cos phi. And E phi will be, E phi is equals to minus eta I naught L e to the power minus j k r divided by 4 pi into j k by r plus 1 by r square minus j by k r cube sin phi. So this is our electric field. Now in the question we were asked to find the far zone fields radiated by the dipole. Now for the far field region, kr is greater than 1. So commonly r is greater than a few lambda. Now so that's why we'll drop the, so dropping the 1 by r square and 1 by r cube terms. From that we will get h theta is equals to minus j k I naught L divided by 4 pi r e to the power minus j k r sin phi. And hv will be equal to minus j k I naught L divided by 4 pi r e to the power minus j k r cos theta cos phi. Just a second guys. So So those who have just joined right now, we are solving the question number 1. The question is a horizontal infinitesimal electric dipole of constant current I naught is placed symmetrically about the origin and directed along the y-axis. Now we have to derive far zone field radiated by the dipole and directivity of the antenna. So we have calculated the far field for H field. Now we are solving it for electric field E, which will be equals to J eta K I naught L divided by 4 pi r into e to the power minus j k r cos theta cos phi, and E phi will be j eta k I naught L divided by 4 pi r e to the power minus j k r sin phi. So these are the the radiated field components in the far field. This is the solution for the part A of question number 1. If you have any doubt in this, please let me know. Otherwise, we will move on to the part B of the problem, where we will calculate the directivity. So I think directivity will be discussed in the next lectures, but I will give a brief idea about what directivity of an antenna is. Directivity of an antenna. So it's a ratio of the radiated intensity, or the ratio of the radiation intensity in a given direction from the antenna to the radiation intensity averaged over all directions. Averaged over all directions. But in the problem we have not provided any kind of direction. So what it means is, if the direction is not given, or it's not specified, so then the direction of maximum radiation intensity is implied. The direction of maximum radiation intensity is implied. So I know a lot of derivations I am doing this for this lecture, this interactive session, but the next one, because then these antenna parameters will be introduced, so we will have lot of numericals to solve upon. But now for this week, the major concept was this only, and if you solve a problem also in these things, there will be so many, it's like a derivation only. A lot of equations will be involved, because the topic is also like that. So now we have to calculate directivity. So the antenna which we are solving here is a dipole antenna, and dipoles are not very directional. That's why you will see the directivity when we calculate it won't be very will be a high number, because dipoles are generally not directives. They radiate in all fields. They are not very. If you see its radiation pattern, it will be something like this. It's a dipole. Let's say this is our dipole. So it will be something like similar like this. It's not a circle, not like this, but it will be something like this in a 2D if I say. So but as we move up on the further week lectures, we will see different kind of antennas which are very directional, whose radiation pattern will be something. Let's say this is one antenna whose radiation pattern will be something looking like this. That means it's very directive along whichever direction it's oriented. So it's based upon the uses, what kind of application we are looking for. We have to see these antenna parameters. Based on those parameters or what our specification, if we are designing one antenna, we first have to specify our requirements. Based on that, the antenna is we have to design. So that's why learning these things are important for the base. Because as we move upon the next lectures, we will professor will be introducing the antennas, and then we will have lot of formulas, and we can use the formulas to calculate. So we will have a lot of numericals to solve upon. But now for this week, I was bounded to solve this derivation because I don't have any other option also. So in the problem we are not specified any direction, so we have to find the maximum directivity in the direction where the maximum radiation intensity is. So for this the formula is, I think this formula will be discussed in the further lectures, so I'm just giving a brief introduction to this. U max 4 pi U max into P radiated, where U max is maximum radiation intensity and P radiated is the radiated power. So radiation intensity is given by U is equals to U naught into 1, I am writing it for our specific case, 1 minus sine square theta for the dipole antenna which is oriented along the x-axis, 1 minus sine square theta cos square phi, and radiated power is calculated using 0 to 2 pi, 0 to pi is the average radiated power along the it's in all the directions due to one antenna, which is U sine theta d theta d phi. It's like solving a surface integral. So which is given by U is U naught 0 to 2 pi and 0 to pi 1 minus sine square theta cos square phi into sine theta d phi. Now we can rewrite this as U naught 0 to 2 pi. First we will solve the integral for d theta. So between the limits 0 to pi 1 minus sine square theta cos square phi sine theta d theta, and then we will solve the phi 1. So when we solve this, we will get P radiated as U naught into 4 pi minus 4 pi by 3 8 pi by 3 into U naught. Now U max we know is going to be the U naught, so the directivity will be 4 pi into U naught divided by P radiated, which is u naught into 8 pi by 3, and when we solve this we will get 3 by 2, which is 1.5. So if you see the directivity when is here, it's 1.5 only, because it's not a very directional antenna, that's why we got 1.5. So I hope this question is clear. If you have any doubt in this, please let me know. If this is clear, we will move on to the question number 2. Now question 2 is repeat problem 1 for a horizontal infinitesimal electric dipole directed along the y-axis. So the question is same, we have to do the same thing, but only difference is this time the antenna is oriented along the y-axis, x, y, z. Now our dipole antenna is oriented along y-axis, and the same I naught current is there. So I hope you understood the previous problem, and you can try this by yourself. So I'm giving this as homework. If you encounter any problem or any doubt during while solving this, you can ask me during the next lecture, next interactive session. So I'm giving this as a homework. So now we will move on to question number 3. So question number 3, the current distribution of a terminated and matched long linear antenna of length L positioned along the z-axis and feed at its one end is given by. So the current is given by I is equals to I naught e to the power minus j k z cap, where z cap is between 0 to L. It makes sense, right? Because the length of that antenna itself is L. So we have to derive expression for the far zone spherical electric and magnetic field components and radiated power density. I hope the question is clear. If you have any doubt in the problem, please let me know. If the problem is clear, we will move on to the solution. Now we are solving question number 3. In the problem, we are given an antenna which is a line wire, we can say it's a kind of a wire, where I, the current flowing over is along the z-axis is I z cap I naught e to the power minus j k z cap, and where the z is between L. So first part we have to find out far zone spherical electric and magnetic field components. Now in the question 1 we have seen that in order to find, if the source quantity is given and we want to find out the radiated field, we need to first find the magnetic vector potential if the current is given. So first we will start by solving for magnetic vector potential. E vector is equals to a z cap mu by 4 pi, and along the length 0 to L I naught e to the power minus j k z cap e to the power minus j k r by r into dz cap. Now in the far zone, the r is much greater than the length of the antenna. What it means is, suppose this is our antenna of length L, and if we are calculating the radiated field at a much higher far location, which is r, let's say somewhere x, y and z. So here this r is much greater than the length of the antenna. That's what the far zone is. We will use r approximately equal to r minus r cap dot r prime. So we can write this r as r minus z cap cos theta, and definitely 1 by r is going to be equal to 1 by r. Because if we take it from the center or from the top of this, if this r or this r won't make any difference, because this distance is very small compared to these distances. That's why I'm considering this as 1 by r is approximately equal to 1 by r. Also, e to the power minus j k r can be written as approximately e to the power minus j k r and e to the power j k z prime cos theta, because I'm writing r as this. So I can now write the magnetic vector potential as approximately equal to a z cap mu I naught e to the power minus j k r divided by 4 pi r between an integral between the limit 0 to L j k z prime into e to the power j k z prime cos theta into dz cap. So what I did here, I took out the r component here because it's not related to the r, so I took it out from the integration, and this ez cap e to the power minus j k z prime was here. So now we have to solve this integral. So in order to do that, let this integral function as I of theta, because it's a function of theta. Now we have to evaluate this. I of theta which is equals to 0 to L integral between the limit 0 to L e to the power minus j k z prime e to the power j k z prime cos theta dz prime. So I can write this as integral between 0 to L e to the power minus j k and z prime are common, so I am taking this out, and 1 minus cos theta dz prime. Now we can write this I of z is equals to, now when we solve this integral, what we will get? We will get 1 minus e to the power minus minus j k L into 1 minus cos theta divided by j k into 1 minus cos theta. Therefore the magnetic vector potential is equals to a z cap into mu I naught e to the power minus j k r by 4 pi r into that I of theta that we calculated is 1 minus e to the power minus j k L into 1 minus cos theta divided by j k into 1 minus cos theta. So now far zone magnetic field, field H is given by, because now we can easily calculate the H field because we have the vector magnetic potential, which is given by minus jk mu r cap cross A. So for the far field, instead of, because we know that it's 1 by mu del cross A, for the far field we can rewrite this as r cap cross A, which is jk by mu into A cross r cap, where A z cap cross r cap is sin theta into phi cap, if you want to write it in the spherical coordinate system. So now the H phi is, means the H field will only have the phi component in the far zone. Theta phi, r and theta components are 0. jk by mu Az sin theta, which is equals to I naught e to the power minus jkr divided by 4 pi r sin theta into, because we know what Az is, so I am substituting the Az value from the previous calculation, which is 1 minus e to the power minus jkl into 1 minus cos theta divided by 1 minus cos theta. And all other far zone magnetic components are 0. Are 0. That means HR, sorry, HR and H theta all are 0. Now similarly we can find the E field. E field is given by E is equals to eta H cross r cap, and here we know that H vector is only the phi component is there, so the electric field is given by eta H phi into phi cross r cap, which gives eta H phi in theta direction, theta cap, it's a unit vector along theta direction, so only the theta component is non-zero for electric field. So E theta is equals to eta H phi, which is eta times I naught e to the power minus jkr divided by 4 pi r into sin theta into 1 minus e to the power minus jkl into 1 minus cos theta divided by 1 minus cos theta, and Er is equals to, and E phi all are 0. So these are the required radiated components, far zone spherical electric magnetic field components for question number 3, where a wire antenna is given of length L, which is positioned along the z-axis, and it's fed with the one end. So if I have to draw this antenna structure, it will look something like, it's a wire at the one end, let's say some kind of connector is connected, SMA connector, which is feeding it with the microwave energy. So this is the wire antenna of length L along the Z direction, oriented along the Z direction. So I hope this question is clear. Now we will solve the part B of the problem. In part B we have to find the radiation power density. So radiation power density is simple. We have studied it before also in electromagnetics, that radiation power density is given by W radiated is equals to 1 by 2 real part of E cross complex conjugate of H, which is 1 by 2 eta. I can write this as, because only theta component is there, right? Or also we can write this as eta by 2 Hv whole square. And we know that the magnitude of Hv square is I naught square divided by 16 pi square r square sin square theta divided by 1 minus cos theta square 1 minus e to the power minus j alpha whole square, where alpha is kl into 1 minus cos theta. And I can write 1 minus j alpha mod square as 2 minus 2 cos phi 2 cos alpha. Also using the trigonometric identities I can write this as 4 sin square alpha by 2. So the radiation power density is W radiate is eta I naught whole square divided by 8 pi square r square sin square theta divided by 1 minus cos theta whole square into sin square 1 by 2 kl into 1 minus cos theta. So this is our required radiation power density. So if the antenna, let's suppose it's radiating the free space, then we know that eta will be 377 ohms, and in that case theta will have to be given and phi has to be given. Only theta is required in this case, right? So we can find out whatever the radiation power density at the particular point at a distance r from the antenna. So I hope this is clear. If you have any doubt in this, please let me know. And question 4, a line source of infinite length and constant current I naught is positioned along the z axis. We have to find the vector potential for this and E and H field components radiated. So this question is also similar to the third question. Now here the length of that wire is infinite. So it's an infinite length wire, feed from one end, oriented along the z axis. Now we have to find the vector potential A in part A, and part B we have to find radiated field components E and H. So this question also I'm giving as a homework because it's pretty similar to the question number 3. You try it. We will definitely discuss question 2 and 4 in the next interactive session. Please try it. If you find any difficulty in solving it, we will discuss it in the next class. Now we will solve question number 5. Question 5. A y-directed Hertzian dipole antenna having length dl carrying a constant current I is radiated in free space, and the magnetic vector potential of the antenna is given by So this question is pretty similar. If you solve the question number 2, then you can easily answer it, because in question number 2 the same thing is there. A horizontal infinitesimal electric dipole directed along the y-axis. Same thing has been asked here, so we will solve this. I hope the question is clear. Now we will solve question number 5. So infinitesimal dipole or Hertzian dipole, both are the same thing. Infinitesimal dipole element is bi-directed so the magnetic vector potential so it's a MCQ. We have given 4 options, we have to select the correct one. So so we are going to write the magnetic vector potential for this antenna, which is directed along the y-axis. Magnetic vector potential will have only y component, correct? And in the option, if you see, 4 options are given. One is directed along the y, another is z. So out of these 4, 2 are directed along the y and 2 are directed along the z axis. So we have to select the correct one. So AY is given by, so definitely there won't be any AZ component here in the vector potential, because the antenna is directed along the y direction. So AY is I naught mu naught I dl divided by 4 pi r into e to the power minus g k naught r. So if you match it with the given options, the correct option is option number C. So the correct option is C. I hope this question is clear. If you have any doubt in this, please let me know. If this is clear, we will move on to the question number 6. In question number 6, a y-directed Hertzian dipole antenna having length dl carrying a constant current I is radiating in free space. So the question 6 is extension of question number 5. So a y-directed Hertzian dipole antenna having length dl carrying a constant current I is radiating in free space. We have to find the azimuthal component of the magnetic vector potential. Azimuthal component means we have to find the phi component. So first we have to write it in the spherical coordinate system. So now we are solving question number 7. So what we have to do here is we have to write from Cartesian to spherical coordinate system. So A theta and A theta and A phi. So we've seen the similar steps in question number 1 also. Which is sin theta cos phi, sin theta sin phi, and cos theta cos theta cos phi, cos theta sin phi. minus sin theta minus sin phi cos phi 0. Ax, Ay, Az, and now we know that this is directed along the y directed, so other component Ax and Az are going to be 0. Therefore A phi is equals to cos phi Ay. All other components are going to, because since this is 0, this is 0, and we have to find A phi, which is minus sin phi into Ax 0, cos phi Ay, and this is also 0. So now we know what Ay is. We have calculated in the question number 6, which was Ay was mu naught ITL by 4 pi r cos phi and into e to the power minus j k naught r. Now we will match it from the given options. If we see, option B is correct. A phi is equals to mu naught IDL by 4 pi r cos phi e to the power minus j k naught r. So here the correct option is option B. So the correct option is B. I hope this is clear. It's we are following the pretty much the same steps what we did in question number 1. So this big derivation was not a waste after all, because if you see all the in the exam also you are not going to get these subjective questions where you have to solve something, but the numericals will be related to the derivations. So if you have derived the formulas, you will remember the steps, so it will be easier for you to solve the this exam problems. Now we will move on to question number 7. For an antenna radiating at 1 gigahertz, what is the distance to the far field region if the largest dimension of the antenna is 1 meter? So the far field region will depends on the dimension of the antenna. Let's say this is we are talking about some kind of a dish antenna. So if the dish is of 1 meter, based on the dimension also that far field depends. Let's say we are calculating at a y, so this distance, is it far field or not, depends on also on the dimension of the antenna. So now we have to calculate what is the distance to the far field region if the largest dimension of the antenna is 1 meter. 4 options are given, and we have to select the one which lies in the far field region for this antenna. So out of these 4, maybe this not be the starting far field region distance. It has to be more than that if it is not the exact same. So now we will solve question number 7. The frequency of operation of the antenna is given as 1 gigahertz. So now we have to calculate the wavelength lambda, which is c by f. C is speed of light in vacuum, 3 into 10 to the power 8, and f is 1 in frequency is 1 gigahertz. When we calculate it, we will get 0.3 meter, and the distance to the far field region is given by the formula. Distance to the far field region is denoted by, let's say, r is given by 2d square by lambda, where d is the maximal dimension of the antenna, which is given as 1 meter. So r is 2 into 1 whole square divided by 0.3, and when we solve this we will get 6.67 meter. So if any option given in the problem which is greater than or equal to 6.67 meter is the correct one. So now we will match the options. So option D is correct. So the correct option is option D, 10 meters. Uh, so I hope this question is clear. This is all for today's session. Like these are the questions that we are solving. So I have given you two questions as for your own practice. If you have time, you can solve question number 2 and question number 4. I will be uploading the solutions also for these problems, and I will upload this video on this. I have recorded the lecture and it will be available on the YouTube also. So the link will be available on the NPTEL website, course website, and my email ID. If you have any doubt, you can ask me over my email. My email is not in ed22d009@smail.iitm.ac.in. You just send me one email. I will surely reply to that. So thank you. That's all for today's session. If you have any doubt, please let me know, or you can send me one email. Uh, that's all. Thank you. Uh, Rakesh, we will definitely discuss it during the next class. Question number 3, right? Okay, I will discuss it in a better way. If you didn't understand it, we will again discuss it during the next class, which is on next Saturday, same time. It's on 30th from 4 to whatever time we will take. Okay, thank you.